What if, when two galaxies collide, they don't eventually merge because the universe itself draws a boundary and says, not beyond this point? For decades, astronomers have watched galaxy interactions, two systems tugging, stretching into tidal tails, then, in many cases, settling into one larger remnant. That's the expected dance, but telescopes also reveal something stranger at the largest scales. Some galaxies appear to approach, grow closer for a while, and then stall. Their relative motion fades, as if they hit an invisible traffic jam. And the most unsettling part? This stalling horizon sits near the scales where dark energy's influence becomes dominant, effectively pushing on the cosmic fabric. So the question isn't just why do mergers slow down? It's what new physics would be required to explain a cosmic boundary that behaves like an eventual limit on how gravity can organize matter? To answer that, we have to understand the merger problem, the expansion of space, and the peculiar repulsion encoded in dark energy. In the before state, the universe is modeled as a competition between gravity and expansion. Gravity tries to bind. If two galaxies are close enough, their mutual attraction overcomes the general stretching of space between them, and the pair falls inward. Historically, we pictured expansion as the background push, while galaxies were islands, obeying their own local rules. For ordinary scales, that picture works well. The cosmos grows larger, but bound systems don't. Then, in the late 1990s, observations of distant supernovae forced an unsettling revision. The expansion wasn't slowing down under gravity, it was accelerating. Something, dark energy, was acting like a persistent, large-scale pressure with negative effect on attraction. With that discovery, the idea emerged that beyond some distance, gravity from one object cannot keep pace with the accelerated stretching. But galaxy mergers aren't just two objects in empty space. They sit in expanding halos filled with dark matter. Still, the key tension remains. At what point does the universe's accelerated expansion cancel the inward pull that would otherwise complete the merger? Here's the core mechanism. Imagine a galaxy pair embedded in a region of space where expansion is described by a scale factor, space itself stretching smoothly. The galaxies have peculiar velocities on top of the expansion, their own motion through the Hubble flow. When they are relatively near, their mutual gravity boosts a peculiar motion inward. Eventually, that inward motion becomes strong enough that the pair decouples from expansion and merges. But if the pair starts too far apart, the background expansion keeps increasing their separation faster than gravity can reduce it. Then their relative velocity stops accelerating inward and can approach a kind of equilibrium. A useful analogy is two magnets connected by a spring, floating in an expanding bubble. The bubble's expansion increases the distance between magnets, even if the bubble grows uniformly. If the spring is strong, analogous to gravity dominating, the magnets get pulled together and the spring compresses until they collide. If the spring is weak, gravity too feeble compared with the bubble's stretching, the bubble expansion wins. The magnets still feel each other, but the gap never closes. They might inch toward each other for a while, but the separation stalls. The system hovers in a balance. In cosmology, dark energy behaves like a smooth energy density with an equation of state that makes its effect repulsive on large scales. In the simplest model, it's the cosmological constant. When you translate that into dynamics, dark energy contributes a term that grows with distance in the same way a repulsive effective force would. Farther objects feel a stronger tendency to separate. That doesn't mean local gravity disappears. It means the net acceleration of the relative motion of two separated masses can switch sign. There exists a characteristic radius, sometimes phrased as a turnaround radius, beyond which the inward pull from the combined mass of a pair is outweighed by the outward effect associated with the accelerated expansion. Now connect that to mergers. A galaxy merger depends on two phases, approach and coalescence. Approach begins when gravitational attraction overcomes the Hubble expansion, converting expansion-like motion into inward motion. Coalescence requires that the inward motion stays large enough, long enough to drive the galaxies into the same halo region where dynamical friction and gas dissipation can finish the job. Dark energy changes the first condition. If the galaxies enter a regime where the universe's accelerated expansion continues to push their separation outward, their orbits can become more elongated and less bound. Dynamical friction, which depends on time spent moving through a dense medium, then becomes inefficient. The galaxies don't spend enough time in each other's inner halos to lose angular momentum quickly. The merger stalls not because gravity stops existing, but because the time frame and geometry needed for friction-driven coalescence are never fully achieved. How was this picture assembled? It wasn't a single discovery, but a convergence. Simulations that include an expanding background show that at late times, the effective repulsion from dark energy increases the escape tendency for marginally bound systems. Observationally, surveys map the cosmic web, filaments, groups, and clusters, and measure how often close pairs show merger signatures. Disturbed morphologies, tidal features, enhance star formation. When astronomers compare pair separations and redshifts, the fraction of mergers doesn't evolve exactly like a simple gravity-only picture would predict. At the largest scales in late epochs, the statistics hint that some interactions never become full mergers. Dark energy supplies a physical explanation. It establishes a moving boundary, a horizon in practical terms, where the universe's accelerated expansion limits the ability of gravity to turn a close encounter into a permanent union. The broader implications ripple far beyond galaxy photographs. First, if mergers stall more than expected, the growth of massive galaxies changes. Mergers are engines for building ellipticals, reshaping morphology, fueling central black holes, and regulating star formation. If the rate or efficiency of mergers depends on cosmological expansion in the way dark energy suggests, then galaxy evolution becomes a clock tied to the universe's acceleration. Second, the stalling horizon makes a subtle but powerful claim. Dark energy isn't only a background parameter that affects distant supernovae. It can scope the future architecture of structures by setting the scales where binding becomes possible. That means the distribution of galaxies we observe today carries information about dark energy's behavior, not just about initial conditions. Third, this frames a deeper question about what we mean by force. In general relativity, the expansion of the universe and the motion of galaxies are not separate stories. They are geometry. Dark energy changes the geometry, and geometry controls whether trajectories converge. Understanding merger stalling, therefore, becomes a test of our cosmological model, a way to probe whether dark energy is truly constant or evolving. If it weren't, the effective repulsion would change, shifting the characteristic boundary and altering merger statistics in a measurable way. So where does that leave us? We began with an open loop. Why would galaxy mergers ever stall? The journey through cosmological balance leads to a crisp answer. Gravity pulls, expansion stretches, dark energy tilts the balance at large scales and late times. There's a characteristic distance set by the masses involved and the strength of dark energy, where inward attraction can no longer fully overcome the outward trend. Beyond that practical horizon, galaxies can approach, interact, and distort, but they fail to coalesce because the conditions for orbital binding and friction-driven sinking never quite materialize. The universe doesn't just expand around galaxies, it negotiates with them. And the most radical part is that dark energy, invisible on the scale of stars, still leaves fingerprints on the fate of entire galaxies. No single collision can rewrite the geometry of the cosmos. If you want more about how the universe shapes itself in ways you can't see, subscribe.